Okay, so I'm going to get started. My name's Ben Smith. I am a Can you hear me? Okay, sorry about that. Don't know why that happened. Okay,
It's all good.
so I'm Ben Smith. I'm a imaging specialist for the University of California, Berkeley. My job involves everything from image processing to building custom microscopes and custom electronics. And so today I wanted to give a sort of breakout session tutorial on basic image processing. And I think especially in light of the talks earlier this morning, this is especially helpful because, it's very tempting to hop on the bandwagon of deep learning and deep learning algorithms because people think, it'll help me clean up my data and make it denoise better. But the reality is most of the time you're not dealing with low information images, you're just dealing with noisy images. In those cases, you don't need deep learning at all. And so to kind of set the stage for that, um, this is a great example, and this is where we're going to head towards by the end of the talk. So on the left is our noisy inputs. This is a real image of some bacteria and trafficking within bacterial cells. And on the right is the output. And this is done using just ImageJ and only Gaussian blur and median filters. So that's the kind of point I want to get across, is get better understanding of how these filters work, what they're actually doing to the information of the image, and therefore how you can solve a lot of your noise issues as long as you have enough dynamic range, just using basic filtering and a bit of critical thinking. And if you have time, I'm also hoping to get to deconvolutions, because actually it turns out the math underlying deconvolutions is very simple once you understand Fourier transforms. And to show you that this type of deconvolution is mathematically possible, and you can do it in ImageJ in one step. It's very fast. But also then through that, to get into why when you try and deconvolve, a microscopy image, you don't get this result where you get extremely high resolution from an extremely low resolution image. Okay. So ultra intro beginner, and probably everyone shows the same slide, to Fourier transforms. So this is your classic Fourier transform equation. And the key thing to get across from this is that Fourier transforms are perfectly reciprocal. What that means is when we perform a Fourier transform, it's completely lossless. So we take something that's an image space and put it into Fourier space. We can take the inverse of that Fourier space and get the image back completely and accurately. So it's not some compression or representation of the image. It's a completely, just like how like rotating image is a transform, Fourier transform is another type of transform, just going from space to frequency. And so this is the classic animation right off of Wikipedia. It kind of shows this effects. This is the classic square wave that people show when explaining Fourier transforms. And so that can be shown as a sum of sine wave frequencies. So it's exact same information, just a different representation of it. So this plot on the x-axis is going to be going from low frequency sine waves to high frequency sine waves. And then on the y-axis is going to be amplitudes. So these two plots are identical. They're just different representations of the same information. And so since we work on discrete images that have discrete pixels, we're not working on continuous functions. We can simplify this so we don't have to do the continuous function integral. Instead, we do what's called a discrete Fourier transform, which is the frequencies are just described as from pixel to pixel rather than continuous. And so to show this, I'll pull this up. I should mention, if anyone has questions, throw them in the chat, because we're just going to keep going. Feel free to interrupt if anything doesn't, if you need clarification on anything. So we're going to try and build a square wave function. So the way to think about this is, imagine this is just like an image, is a plot of intensity across the width of our image. So to set up a basic square, we have everything from low frequency sine waves all the way up to high frequency sine waves. And so if we start summing these, we're going to try and make a square wave. So you can see right now, we have the basic premise of our square wave, where we go from high intensity to low intensity to high intensity to low intensity. But you'll notice that, well, the edges aren't that sharp. We're kind of gradually going from a low intensity to a high intensity. We want like an instantaneous jump from low to high. So we think about it, it's like, well, we need a higher frequency sine wave, right? Because high frequency sine waves have steeper edges on them. So what we can do is we can add a slightly higher frequency. So you can see this is our fundamental. This is twice the frequency. You can already see we're starting to flatten out the top and the bottom, and our transition is also getting steeper. Now, as we continue to add more and more terms to our square wave approximation, you can see our edges keep getting steeper and our top and bottom keep getting flatter. And so from here, so now you can see if we add sufficient numbers of terms, we can get a very steep transition and very flat top and bottom. So this would be like, say, an intensity profile across your image, and this would be the corresponding Fourier transform. The summation of all these sine waves creates that. It's like, well, that's a really weird representation. Like, why would we go through all this effort to describe an image as a sum of sine waves? Okay. So to show this in image J, we're going to pull up image J. And so just as we described, here we have two rectangular bars going from bright to dark to bright to dark. And like I said, if we take the intensity profile, we can see that we get exactly the same square wave function we were describing before, right? It goes from high intensity to high intensity to low. And so now we're going to take the Fourier transform, and we can see this looks very similar to the spectrum. It's just a mirror image of it, right? So it goes, we have the highest peak right in the middle, and then we get lower and lower terms. So in this case, the amplitude, the height of that frequency is the intensity of the pixel. And it goes down to lower and lower amplitudes, exactly as we see in our spectrum here. Okay. So any questions so far? Okay. So to better understand how to look at these 2D Fourier transforms, to kind of orient ourselves so from our center point, as we go out towards the edges, we're going to higher and higher frequencies. Those are higher and higher frequency sine waves. And since it's a 2D, we also now have direction. So as we go out on the horizontal axis, we're getting higher and higher horizontal frequencies. And as we go out on the vertical axis, we're getting higher and higher vertical frequencies. But as our image didn't modulate on the vertical axis, there's no spatial frequencies in the vertical axis. There's nothing ever changed. And there's a key spot right in the dead center, which is the DC component, which has no frequency. So what is that and why is that there? So the catch is a sine wave, right? If you integrate over a sine wave, it integrates to zero, as it goes both positive and negative. In regards to an image, this makes no sense. You can't have negative photon counts. So at the very least, we know we need to add an offset to our sine waves such that they minimize at zero. So now zero is the lowest intensity we can get. So you can see what we have to do is we have to add a constant term. And right, so the constant term has no frequency to it, and therefore that's the DC component. And additionally, we need to be able to distinguish between, modulation of so this would be a very bright image where even the background is very bright. This would be a dim image where the background is very dark. And so the offset also helps us distinguish these. So the way to think about this center point in your Fourier transform is it's effectively the mean and represents the mean intensity of the full image. So now with just that, we can get to our first application of Fourier transforms, which is actually really helpful a lot of times when taking confocal images or microscope images, which is we can really quickly infer the resolution of our images. So In this case, we have an image of diatoms, and here's our Fourier transform. And so we're going to pull up the image here. And the key to doing this trick is you see our image is scaled. So this is important. So if you're not familiar, just go to Image, Properties, and here's our scaling information. So as long as we have a scaled image, if we run the Fourier transform, effectively what your resolution is it right? It's the finest detail that you can resolve, that you can distinguish above background. So how close 2 points can be. So another way to think about that is it's the highest frequency, right? So there's a point where your sine wave gets so fine that the peaks on your sine wave, you can't distinguish them anymore. So the way to think about resolution is you're really asking, what is the highest frequency sine wave? What is the sharpest edge that we can resolve? And so now we can go out onto our Fourier transform, and we're asking, so here's our background noise. So these are very, very high frequencies, but we have no signal out there. So this is the actual modulation above background in our image. So by simply asking, what is the highest frequency above background? So let's take my cursor out. And so here we can see at about, so if you look up at the title bar up here, you can see about 230 nanometers per cycle. So that simply, just by using a Fourier transform, we can real quick assess what is the actual resolution of my image. And this is especially helpful if anyone does confocal imaging, where you can often run into an issue where your Z resolution is going to be a lot lower than your XY resolution. And so using these Fourier transforms, you can real quick address whether your resolution is isotropic or not. Okay, looks good so far. So any questions? No.
Oh, there's a question.
Yep.
It's Abil might ask it in chat, or if you want to say in video, that's also okay. Okay, the question is this different than create a point spread function, PSF?
Ah, that's a really, really good question. Hold on to that for just a little bit. It's actually, it's very similar. And when we get into convolutions and deconvolutions, we'll be able to answer that in a lot more detail. So I'll say just hold on to that for a few seconds. But very, very good question, and actually really good insight about Fourier transforms. Okay, so here's some more Fourier transforms. In this case, our intensities are sine waves. And so we already said that the further out you go to the edge of your two-dimensional Fourier transform, the higher the frequency. So in this case, we can see a very low frequency sine wave, and therefore the peak amplitudes we're seeing are close to the DC point. That means they have a low, relatively low frequency. And then here we have a higher vertical frequency sine wave. And so we can see on our vertical direction axis, we have two peak points that are further away from the origin, which is telling us that there's a high frequency sine wave. And in fact, we can tell that the images are even sine waves without even looking at the images themselves, because that's the only way we get these single peaks in a Fourier transform is a perfect sine wave. So now that we have the perfect sine wave, well, we can try rotating at 45 degrees, and it falls apart. And it's like, whoa, what happened? This is pretty straightforward. Sine waves, you get points in your Fourier transform. And so you see this in most of your biological sample Fourier transforms. You're always going to see a horizontal line, almost always see a horizontal line, a vertical line in your Fourier transform. And this is due to the edge effect. And this is the fact that Fourier transforms, a sine wave doesn't have a begin and an end. They're infinite. They're a continuous function that goes off to infinity. And so to describe an image as a sum of sine waves, you have to assume that the image itself is a recursive function that goes off into infinity. So you can see now when we try and tile this image, where one image ends, the next one begins, we suddenly have what looks like a square wave, a very sharp jump. And that also shows up in our Fourier transforms. This is a combination of the main sine wave in the Fourier transform, as well as the results of that jump. Okay. So here's what you'll more often see in real images. So you can see we've got this cross pattern in your Fourier transform. And so this is purely an artifact. So this is generally something you need to ignore because it's just due to the image tiling. So if we tile our image and then take intensity profile, we can see that we have a very sharp jump in intensity as we go from one edge of the image to the other. So once this image tries to repeat. And you can see that sharp jump is specifically only in the horizontal direction and only in the vertical direction because our image is a square. And therefore, we see that sort of square wave pattern, the horizontal line, vertical line in the Fourier transform. Just a second. Okay, sorry about that. Sorry. Okay. So now we have 3 sample images. And so you can see we have an image with a circle in the middle, image with circles at the edges, an image with circle at 2 corners. And so now I can ask you guys, out of these 3 images, which ones would you expect to show an edge effect? And you can type it in the chat. No brave souls. Okay, we got a few guesses yet. So a lot of people are guessing circle 3, which is good. So if you look at this, so if you tile circle 1, right, we can see when we transition from one image to the next that there's a smooth transition at the boundary because one side of the image matches the other side and the top and the bottom match, so there's no jump. It's just the image of the circle. So if you take the Fourier transform, we see no edge effect. We don't see the vertical and horizontal lines. And same thing if you take the second image, we can see no edge effect, and correspondingly, when we tile it, one edge perfectly matches the other. So it looks exactly like our circle pattern, just offset to the edge. However, if we take our third image and tile it, we can see our edges don't line up anymore, right? So now we have both the circle, but the circles also have a flat edge on the top and the side. So we take the Fourier transform of this. Now you can see we get the vertical line and the horizontal line because our sides of our images don't match up anymore. Okay. So that's the case sometimes in your imaging where you might not see an edge effect is if you have something in the center of your field, but all the edges are dark, then you might not see the edge effect. But most of the time, your images will run all the way up to the edge, and therefore you'll see those 2 lines in your Fourier transform. But the general rule of thumb is just you kind of ignore those. They're an artifact of the fact that the image is a recursive function. Okay. So here's some more Fourier transform. So hopefully how you go from this Fourier transform, the relationship between the image and the Fourier transform starts to become a little bit more intuitive. So in this case, we have a brick wall pattern. And you can see we mostly have vertical edges. So we have the sharp edge here for every row on our bricks. And we also have these sharp horizontal edges. So some of our vertical lines have a horizontal edge, they have an edge in the horizontal direction. And correspondingly, we only see information or Fourier transform in the horizontal and vertical axes. And correspondingly, if we look at this image of sugar cubes, we get this kind of splayed out pattern. And each of these edges is going to correspond to one of these lines. In fact, you can see like this edge right here is going to be this line right here, right? Because the edge, so basically the direction of the edge, the line in the Fourier transform is supposed to be orthogonal, because that's the transition, the sine waves are going this way to encode the edge going this way. And then correspondingly, we have a slightly rotated edge here, which would be this line in the Fourier transform right here, and so on and so forth. So this is kind of cool, because now, hopefully by this point, you can start to see the relationship between a Fourier transform and what is it's encoding in your image. Okay. And then for a little bit more complex patterns, so here's the letter Z, and you can see we have this diagonal line right here, which is going to be this line right here in our Fourier transform. And then we only have vertical edges after that, which is going to be that line. Here we have a B, which is round, so we're going to get edges in all directions, and so on and so forth. The K is really nice because we have two lines off vertical, and we get the two corresponding lines in our Fourier transform. Okay, so now that we have a rough orientation of Fourier transforms, we can start using them to our advantage and actually start doing image processing in Fourier space and get information out of that. So here's our image and its corresponding Fourier transform. And so what we're going to do is we can remove the low frequency information. And so remember, low frequencies are going to have things that have smooth transition, so not sharp edges, not fine detail, right? Because fine detail requires very high spatial frequencies. So by removing the low frequencies, we'd expect that in this image, right, so the background would be very low frequencies, very blurry and very smooth, but the foreground is very sharp. It's very fine detail, so it'd be mostly high frequency. So so by doing this, we can then take the inverse of this Fourier transform and see what image do we get. Whoops. Oh, that's good. Oh, I saved the image. Just a second. Try and get back into this. Sorry, technical details. Okay. I don't know what I say. I'll just use my hand. There we go. So you can see by taking the inverse of our sharpened image, so remember we removed just the low spatial frequencies, we now got an image where all that smooth blurry background's removed. And we're getting predominantly just the foreground, all the sharp details. Now, one caveat is if we then take the Fourier transform of this image, you'll notice we don't get this Fourier transform back. We can see where we cut out all those frequencies, but you can see we still have information there. And the key thing to remember is it has to cheat a little bit because our image can't go negative, right? It's an 8-bit image. And so as a result, it can't actually have zeros. Now, especially like the DC term. So the center term is the average intensity of the image. The average intensity is still non-zero. And so what the algorithm has to do is it kind of fudges it. It goes, okay, what is the lowest I can possibly put these frequencies and yet still encode 0 and above? There's still not, how low can I get it and not have my image have to go negative? So just keep that in mind is when you excise it, it'll go as close as it can to what you asked, but it can't go negative. So it's a bounded result. Okay, and correspondingly, we can do the inverse, where we can remove high frequencies, and the end result is we get a blurred image, right? So by removing all the high frequency information, now we only have the very lowest frequencies. We can see that we lost all our sharp detail and basically lost all of our detail in the image. And if you take the inverse, we can see it's much more effective. So, right, because there's no fudging correction that needs to be done, it's a purely smooth image. And so you can see we have this nice, perfect pattern of the original Fourier transform. and then just goes down to our background noise level with the horizontal artifact. So that's the edge artifact we talked about before. Okay, so any questions about high pass and low pass filters? Good.
None so
Okay.
far.
So one thing you might have noticed when I did this trick is what's called a ringing artifact. And so you can actually see the sort of repeating sort of ripple going across the image when I did this filter. Interestingly enough, if you've ever done phase contrast microscopy and you see the halo on phase, it's for the exact same reason. It's when you have a sharp edge removed in Fourier space and your phase plate sits on the focal plane of the image. So that's like another really important point is that Fourier transforms aren't computational. Microscopes are doing Fourier transforms all the time. Uh, and that's why our focal planes are so stacked with so many components. So if you go back to our original, nice, clean, one-dimensional, we can see that same ringing artifact here. So we get the sort of overshoot and undershoot at these boundaries. But you can also see as we add more and more terms, that overshoot and undershoot start to get tighter and tighter. So what's happening is we're cropping the highest frequency, and past that highest frequency, we don't have even higher frequencies to try and tighten that over representation of the highest frequency sine wave. And so as a result, wherever our Fourier transform is cropped, we get this overshoot. Okay, so how do we get rid of this? So the way you get rid of this is actually the same way you get rid of this in phase contrast microscopy, which is you use what's called an apodized filter. So the problem is caused by the fact that we have this jump of all these frequencies are highly represented and also nothing. But instead, if we smoothly round off and transition from the data we want to keep to the data we want to filter out, then we can actually suppress that ringing artifact. So here we have our dandelion image again, our same reference image. In this case, we're going to try and blur it. So I'm going to set my large structures. So this is our high pass filter. But this is our low pass filter. So I'm going to set this to like something arbitrary. I'll say 10. And the key thing is you want to see the filter. You want to see the filter is going to apply. And so the nice thing about this bandpass filter tool in ImageJ is its filter is always apodized. So if we hit OK, we can see we blurred our image. And you can see instead of just having a sharp cut, so instead of keeping the low frequency image and also boom, cuts it out and gets rid of all the high frequency, this is the apodized filter. So the way I think about this is what it did is it took this function and multiplied it by the Fourier transform. So these frequencies were kept the most, and then we suppressed more and more and more until all these frequencies were almost completely suppressed. And so the end result is now we're blurring our image, but you can see no ringing artifacts. So that's a huge advantage of apodized filters. And the key thing to know is just that filter is right here, the bandpass does it for you. One thing you'll see in the bandpass filter tool that can be helpful, especially with certain cameras can run into this issue, or if you're having issues with your detector, is to suppress stripes. So here we just ruined our image. So now we have all these specifically vertical lines. We'd be like, wait. In Fourier space, the nice thing about all these lines is they're all going in a specific direction. That means all their edges are going in a specific direction. So if we suppress frequencies only in that direction, then we can kind of cut out these lines, and get back as much of our image as we can. And so there's a tool built in for that. And in this case, I only want to count the lines. So I'm going to set my small structures to 0 and my large structures arbitrarily high, which basically means don't filter any frequencies with this image. What I am going to do is suppress the vertical stripes because our stripes are going in a vertical direction. I'm going to say OK. And you can see we've dramatically removed the stripes. And this is far better than like trying to excise the stripes or any other method, because the problem was it was the stripes plus our image. So we also want to get the image back that was encoded underneath those stripes. To do that by hand is basically impossible, right? Because you'd have to figure out what the convolution is. So this is the filter, so this makes sense, right? So the filter, it removed all the spatial frequencies in the horizontal axis, which is removing only edges that are perfectly vertical. And you can also see the one thing it did for us is right in the middle, it kept that DC term, right? So that means it preserved the mean intensity of our image as well. Now it's not perfect, right? Because the image also had information coded on this. So we do get these sort of streaking artifacts, but the streaking artifacts are far less than the original lines we had.
Hey, Ben.
Yep.
Tommy asks, what if the stripes are diagonal?
Okay. So the catch is that is if you go to, go to filters, the bandpass filter only assumes vertical or horizontal, but that doesn't mean that's all you can filter. And actually someone already had a pretty good recommendation, which does work, which is you could rotate this, you could actually just grab the filter it generated and then just rotate it to the arbitrary angle that lines up with your diagonal lines. So the way you do that, one of the easiest ways you do that is, it'd be hard to draw perfect diagonal lines, but say you had a line like that. Let's just draw it. So say we had a line like this. What you could do would be to measure the angle of that line. So in image J, one of the easiest ways to do that is just use your selection tool. Go along. If you just look up at our title bar, when we draw that, it gives us the angle. So it's saying our angle is 132.4. So we can just go to image, transform, rotate, and we want 132.4. Let's go the wrong way. So it'd be 132.4 plus 90 or minus 90. So that's going to be 42.4. So the one catch to this, you can see it's cropped off our corner. So what I would actually do is I would have it make the filter on image twice as large, right? Which will give you a Fourier transform filter that's twice as big. And therefore you can remove just the middle region. And then just like I saw when I drew a selection on the Fourier transform and then removed it, you can also just multiply your filter by that Fourier transform. Just to set all the background values to 1. And so this is super helpful. Actually, I've done this plenty of times where if you have features exactly in that case, where you have features that are predominantly oriented in a specific direction, you want to suppress them, this absolutely works. Sometimes you'll have to fan out the tolerance a bit because biology doesn't tend to go in perfectly straight lines. But you can definitely suppress edges within some variance. So usually I'll just, all you need to do is preserve the 0. So let's write a block of code that will draw like some arbitrary selection, a wedge sector selection to suppress all edges within that bound. But yeah, so that's how you can do diagonals, and also diagonals that are not perfectly lined up. Okay. So next we're going to get into one of our first filters in ImageJ, which is the Gaussian blur. And Gaussians are very special when it comes to Fourier transforms. It also goes with how do we do a perfectly apodized filter. And the key thing with Gaussian functions is Gaussian functions are perfectly reciprocal in Fourier space. So the Fourier transform of a Gaussian function returns a Gaussian function. So to see that, so the first thing we're going to look at is the classic thing you've seen, which is what does a Gaussian filter do, right? So Gaussian filters, so it's under your filters, the classic Gaussian blur, right? So if you run a Gaussian blur onto our image, right, it blurs it out. So it makes it seem a lot smoother. And so as you expect, we just removed all the sharp edges. So if you look at the Fourier transform original, you can see we have both high and low frequency information. But if you look at the Fourier transform of our blurred image, you can see we've completely suppressed all of our high frequency information, and you can see we only have left this little bit of low frequency information. So hopefully by this point, that seems a lot more intuitive that all these sharp edges are gone, they're smoothed out, and therefore we don't have high frequency information anymore. Okay. So in this case, what I've done now is we have a Gaussian function. So just a pure Gaussian function. And if we look at the intensity plot profile, you can see this is indeed a Gaussian function. However, if you just go straight into image J and you take the Fourier transform of that function, does this look Gaussian to anyone? I can tell you it doesn't look Gaussian to me. And this has to do with how image J conventionally, actually how most programs are going to conventionally show Fourier transforms. So they show it as a power spectrum. So it's actually the log of the Fourier transform. So what we need to do is if you go into, so if you want the real Fourier transform, if you go into Fourier transform options, we can get the non-log, so the actual real Fourier transform. So we're going to say okay. And so now if you go to process FFT and take the Fourier transform, aha. So this is the actual Fourier transform of that function. If we plot its profile, we get a Gaussian function back. And in this case, right, so if we made this Gaussian very small, which means it's a high frequency Gaussian, then the Fourier Gaussian would get very wide because if it's a sharp Gaussian, it needs high frequencies. So it's kind of cool. These two Gaussian functions become inverse widths of each other. And so to get back to this image, we can just simply, if you just go to math, we're going to take the log of our Fourier transform. Log, there you go. And there you go. So like, hey, that looks exactly like this. So the key is the default Fourier transform representation in image J is the log of the Fourier transform. If you're like, well, you know, geez, Ben, that's a weird representation. Why do we do that? Well, if we go and grab a standard image, so come back to this image again, and we're going to take the raw Fourier transform of it. So we go back to FFT options, raw power spectrum. All we get is a DC component. That's all we can see. So if you zoom way in, that's all we see. That's it. Because the amplitude of the mean intensity of the image is far greater than any of the spatial frequencies in the image. And if we try and adjust, the brightness and contrast to try and see those lower frequencies, we can only see the central terms because there's such a huge dynamic range between the low frequencies relative to the higher frequencies. So therefore, for most images, the raw power spectrum is useless. It's great for analysis, not so great for visualizing the Fourier transform. So instead, if we kind of think of plotting it on a semi-log, which is what we're doing, we're going to go back to math, take the log, and now we get the Fourier transform we're used to. So that's just one other thing to keep in mind is the Fourier transform representation by default is the log. And it's because the raw Fourier transform just looks like a point. You can only see the DC component. Okay. So any questions about Gaussian?
None yet, but they might
Cool.
show up and I'll let you know if they do.
Yep. So here's one application of using Gaussian blurs to your advantage. So if you look at this movie, you'll see the very first frame, the cells are in focus, they're sharp, but then as the movie progresses, they're going more and more and more out of focus. Oh, I saw a question about median, and that's also really good. We're going to get to median next. Yeah. So it's going sharp to out of focus. So if you look at the corresponding Fourier transform, we can see exactly that effect. We can verify it. So we can see in the very first frame of that movie, we have high frequency and low frequency information. But then as that movie progresses, we lose our high frequency information and only get lower and lower spatial frequency information. So that tells us by just looking at the Fourier transform, we can tell our image is going out of focus. Now this causes problems because say you want to, in this case, we want to track these cells, Well, when you try and come up with some feature space definition of what a cell is, well, it's changing as the movie progresses. So no, it's like it'd be so hard to come with an algorithm that can come up with definitions that work for both in-focus cells and out-of-focus cells. So we can make it easier and just go, well, let's just make the information the same for every single frame. And so the way you can do that is just by running a Gaussian blur. So now we've blurred that exact same movie. And if you look at our Fourier transform, we can see the resolution stays constant. Notice the information content of the image is constant. And so you'd be like, well, the image doesn't look that good. And like, well, for us, it's nice for it to look good, but for a computer to find objects or to, come up with a mathematical definition of some feature, it's best to keep it consistent so that, whatever definition you come up with is the same in every frame. So by doing that, you can now see in the end, we're able to come up with a tracking algorithm that could track all these cells. So this would be entirely impossible or nearly impossible without having done that blur, but by making the cells equally blurry in every single frame, now we can segment them out. It looks like there's one question.
No, I think we're good.
That's this comment. Yeah. Okay. So now that we've have a sort of good sense of Gaussian blurs, now we can get into the combination of Gaussian blurs with image calculator and do some really cool tricks. So like here's a classic one, which is to combining a image with a Gaussian blur to do a high pass filter. And so to kind of show this effect, we can grab this image. So here we have an image, and we want to have just the dandelion fluff and not the background. But the problem is it's not simple. You can see the background through the fluff. So if you want to think about trying to solve, oh, you can definitely comment. Yeah, sorry, no worries. So if you tried to like solve this in position space, it'd be a nightmare. You'd have to sit there, grab your, arbitrary selection tool and like try and cut out all the background by like you're never going to do it. It'd be prohibitively time consuming. But in Fourier space, it becomes exceptionally trivial. Right? So what we're going to do, we're just going to go to, we duplicate our image. So what we can't come up with just a simple excision, but can come up with like, what is the background? So what is what we want to remove? So the way you can do that is we can go to Process, Filters, Gaussian Blur. And what we want to do is this, you can do this purely subjectively. We want to find an amount of blur that changes the fluff as much as possible, what we want to keep, without changing the background, which we want to get rid of. So you can see we're changing the fluff a little bit without changing background, so we can go higher. We still haven't changed the background. We changed it just a little bit. Now I can try 20. See, now we're starting to change the background. See, the background's also subtly getting blurred as well. So that tells us we went too high. And so we'll try 10. And so now we have the sharp fluff, and now we have a background representation of the image. So by simply saying, this is the high frequency plus low, this is low, so this image minus this image should give us only fluff. So we can go to image calculator, take our original image, subtract the blurred image, and boom. Something that would have taken years and years and years to do by hand, we just did almost instantaneously using Fourier space, because it's a trivial problem to solve in Fourier space. And the reason it's trivial is because we had very sharp differences between our high frequency information we want to preserve and the low frequency information we want to remove. You can also see our excision was actually even better, because one thing you can see here is this is what's called purple fringing, which is actually an artifact from photography. And so you can see we're also able to extract the purple fringing artifact from the original image, which is in the original image is convolved with the background. So we effectively just did a deconvolution, a very simple deconvolution. We'll get into more elaborate ones, but this is like the simplest one, is by simply subtracting low frequency information. Okay. So another cool application of that trick is,
There's a question then.
Yep.
Does this background subtraction change the pixel values of the in-focus
It
object?
absolutely does. And that gets to a point that's really great to make about image processing, which is whenever you're processing an image, you're always removing information. And that's really important to keep in mind, because if you didn't collect much information about your image to begin with, say you took an 8-bit image, but even the highest intensity is only 100 pixel values, as you start to whittle away more and more information, you have nothing left. Your signal looks practically binarized. And this gets to a really important point, which is why you want to collect your image, which is as much dynamic range as possible. Even if it's really dim, just turn up your ADC gain on your camera or your photo multiplier tube just to measure it as finely as possible. Because yeah, as we're cutting away, so we're trying to do like surgery on our image. We're trying to whittle away all the information we don't care about, which is the noise in the background, and get that kernel in the middle, which is the signal we do care about. So yeah, you're always removing information in image processing, which is really good to be aware of. So here we have a focus series taken on a epifluorescent microscope. So not a confocal. We just put a sample, this case is a cross-section of a retina, and took images with a motorized Z stage. And this is like a classic trick that a lot of people don't realize is you can do a three-dimensional reconstruction pretty quickly on compound microscope images. So all we had to do is just take this image, this movie, do the blur, right? Because effectively the out of focus background is just low frequency information. And therefore, what we want to preserve is high frequency information. So we could do the exact same trick. We can just remove the blurred equivalent of this. And the end result is we can get a three-dimensional image. So basically a fully in focus image with no elaborate deconvolutions or iterative deconvolutions, simply by just using the Gaussian blur and subtracting the blurred image from the original. So what's really nice about this trick is you can, a confocal microscope takes far longer to take a single image than a epifluorescent microscope. And therefore you can collect far more samples with an epifluorescent using this simple trick. I should add one caveat, which is this trick works because the remaining information in the image is purely high frequency information. It's neurons, it's fine detail, sharp edges, membrane bound stuff. If your image is a smooth or large solid object, then this trick will not work, right? Because if it's a smooth, round, solid object, then there's low frequency information that's filling the center of the object. So it just takes a bit of knowing about your image to know whether or not just simply removing a blur, or for those solid objects, then you have to do a real deconvolution.
So you got another question.
Yeah.
Can you back translate, such as superimposing or overlaying, low and high frequency information back to the original image?
Oh, absolutely. In fact, that gets to another filter. There's another filter that's sort of does that. So like one is, right, you could, by simply just taking a blurred image and the result of the image calculator and sum them back together, you get back to the original image just by adding them together. There's another type of filter called, it's in here, unsharp mask is what I'm looking for. There it is, unsharp mask. So unsharp mask is doing something very similar to that, where what it's doing is it's taking your original image, it then takes a sharpened image, and it adds the sharpened image back. And you can actually adjust the weight, which is how much you want the sharpened image to be weighted relative to the original background image. And I see one other question, which is this similar to extended depth of field? And actually, extended depth of focus is a true deconvolution, rather than this, which is we're just doing a, well, this is also deconvolution, but we're deconvolving based off of just a Gaussian function, versus extended depth of field functions actually deconvolve with the point spread function, which is we'll get to at the very end. So no, actually, extended depth of field is a deconvolution with the point spread function, or an estimation of the point spread function. Okay. So now, which someone already asked about, which is the median filter. So median filter is a very powerful tool. So
Quick
a
question
median, yeah.
before you move on to this, but it is similar to the top hat filter, right?
Not familiar with the top hat filter. I'm familiar with top hat functions. I'm not familiar with the top hat filter, so I wouldn't be able to answer that, unfortunately. Okay. Unless it's the difference in Gaussian's filter. Anyway, so next up is a median filter. So those familiar with like confocal imaging, the median filter is very, very powerful for removing salt and pepper noise. And so here's a simple visualization of what median filter does. So in this case, I have a heat map of our pixels. Remember that, when we look at an image, the image is just a representation of a matrix of measurements. The reality is your pixels are actually, measurements. It's a grid of measurements. And so here we have the actual grid of measurements represented. These are each pixels, but they're represented correlative intensity. And so we can see we have this disproportionately high single pixel, right? And so if we, convolve it with its neighbors, so say we look at Gaussian, it's just going to spread it out. So everything's going to become brighter. It'd be nice to like just cut this out and go like, well, let's just replace it with, it's most likely its intensity with something similar to what its neighbors were. And that's exactly what a median does, right? So all a median is going to do is it's going to take the surrounding values, rank them from largest to smallest, take the middle value, and return that back. So the end result is, rather than spreading out the hot pixel or the bright pixel, it just cuts it out and replaces it with the best approximation from the background. Okay. So the key thing to keep track with this is, what is it actually doing to our image? And we can then answer that with Fourier transforms. So here's our original image. If you run a median filter, so this is very high background image. But the key thing is it kind of looks like it got blurred out. But let's look at our Fourier transform. So we can go to FFT.
Ben, when you get the chance, could you also blow up the two images just a little bit?
Oh, yeah. Thanks. There we go. Also shift the contrast. There you go. It'll be easier to see. Yeah. Okay. So if you look at the Fourier transform of original, so here's the original image. And let's see what happened when we took the median filter. So it did something very different than what the Gaussian was doing. So if you look carefully at this, we can see that there's 1, 2 notches now missing. It actually kept the high frequency, the highest, the sharpest details preserved with the median filter, which is good to know. And instead, it actually took notches out of our Fourier transform spectrum. And in fact, I can tell you that this was a median filter with a kernel size of 2, because it has 1, 2 notches. So if I go back and I take the median filter, so I'm going to filters and go to median, and I take one of 3, and we take the Fourier transform of that, we can now see we have 1, 2, 3 notches removed from our Fourier transform spectrum. So this is really important to know. So one thing this is important to know is, clearly, right, the larger your median filter becomes, the more and more information you're chopping out, right? Because you're chopping out more and more of these notches from a Fourier transform spectrum. But the other helpful thing to know about the difference between a median and a Gaussian filter is that you can see it's doing a much better job at preserving high spatial frequencies, right? Gaussian it solves removing information by just removing it from the outside in, versus a median filter removes it by removing these concentric bands, these notches from the Fourier transform. Okay. So this is our library of standard filters. So this is kind of getting to better understanding of what are these filters doing. So here's our original signal. You can see our Gaussian it's very much like sanding. It kind of sands off the edges and rounds them off, as we expect, because it's a purely a low pass filter. So it's removing any sharp transitions. Our mean, you can actually see it keeps sharp edges. There's a sharp edge here and a sharp edge here, because you suddenly transition from no image to it's now the mean of the ramp. So you get this ramp effect. And you can see in this case for the median, we got pretty much the exact same image back, which makes sense. As our median kernel, so it's going to be a square that's looking within to take the median, if more than half of that square was off our circle, it's just going to return a 0. And if more than half that square is on the circle, it's going to return 255, the maximum intensity. And so the end result of that is it's going to just effectively turn the same object back. So this is including the very, very sharp edge of the original image. So in terms of Fourier space, so in this case, we now have our, we added some classic salt and pepper noise to our representative dandelion image. So here's our original Fourier transform. And as we discussed, if you run the Gaussian filter, we just remove high frequency information. So we basically unsharpened it. And this is where it can be really deceptive, where to our eye, the mean looks very similar. It just looks like a blurred out version. But when we look at the Fourier transform, we can see the mean is very different. And this makes sense. If you think about a ramp, we had that sharp transition from 0 to coming up that incline, and very sharp transition coming from up the incline to going across the top. So we know it has high frequency information left in it. And you can also, should be able to tell me now, the size of our mean must have been 2. So the size of the kernel is 2 because we have 2 notches taken out, which is very similar to what the median filter does. And then in terms of denoising, we can see the median filter was the champion, because these two filters, what they're going to do is they're going to take that salt and pepper noise and spread it out and kind of smear it. It's spreading the contamination, as opposed to the median filter, which is effectively replacing that contamination with what is the best representation of what its neighbors were. So now we can see we get a very clean representation of the original image, but it's not the original. So we can already tell it's, we can't see the fluff quite as well. And that's because we did still remove information from the image. We still removed these 2 notches from the Fourier spectrum. Okay. So now we're going to get to a real world example. So this is, I was really hoping to get to as my sort of, counter argument to Yuri's talk, which is, really important to talk to, because, one thing he kind of failed to mention was he was not just solving a noisy issue, he was solving a low information issue. And so, when you use deep learning, the way you solve low information is you're convolving your guess of what the data should look like with a little bit of information that you have. In other words, the final representation is a mix of your model and the data. But as long as you have a lot of information about your image, including a lot of information about the noise, and there's as long as you took a high dynamic range image, a nice 12 or 16-bit image, you don't need adaptive learning or any of that. You can just use basic filters and go from an image that looks like this to an image that looks like this. And so we're going to go through that step by step. So here's our noise example. And I can keep my little cheat sheet up. And this is actually really good practice when you're trying to process an image and remove noise. As you can see in my little cheat sheet is actually the file. You can see it has this sort of list on it. It says 10 blur high pass, 2x2 median, 1Z median. And so whenever you're trying to figure out how to filter out noise, it's always good practice to save every step with the name of what you did. Because a lot of times you'll find, especially order matters. So you'll start removing noise and you'll realize, oh, shoot, I got to a point where my background noise now looks the same or has the same feature space as my signal. And so then you want to be able to go back to an earlier step and try and change the order, but you don't want to go all the way back to the beginning and try and remember everything you did. So just by saving step by step, by the time you get to the final solution, literally the name of your file is the solution. It's the order of steps you need to do. Okay.
You've got a question. How would you generate a histogram of all pixels with all frequencies plotted and back superimpose this information back to the original image?
Oh, that is a really good question. Yeah, I did not get into that. So if we take an image, oops, no, just the image. Okay, and I take the Fourier transform. And this actually gets into why we always want to do our image processing in Fourier space and never in the original image. Because if I go in here and start cropping out things I don't like, right, that's unethical. You can't go, oh, I want to remove that cell, but keep this cell. And so the safest thing to do is the fact that a single point in the Fourier transform corresponds to a sine wave going all the way across your image in that direction. So one point in the Fourier transform corresponds to all positions in the image. It's the frequencies that contribute to all those positions. And then correspondingly, one point image, it takes the entire Fourier transform to back calculate, right? You have to sum all these back together to figure out what the true intensity is at that point. So there is, so that's the beauty of doing this Fourier transform processing, is you get, if you do things in the frequency space, it's going to always do it uniformly to the entire image. So I can't look at this pixel and go, oh, that's this point on my image. You can't do it. Then one follow-up question that you might ask is, well, we have an issue, which is, how does a Fourier transform distinguish between, an image like that an image like this? It's the same frequencies. So how do you then encode positions, translation of something? And so what's not being shown to you, you can get it by going back into the FFT options, and it's the complex Fourier transform. So the other piece you need, should we actually go back here, so you can go to mag phase view, is the phase, right? So the phase, you can see as we change the phase, so I'll actually clear this, right? So if you take any given sine wave, right, the phase translates that sine wave side to side. So effectively, phase encodes the position of that sine wave. But the problem is it's not that intuitive. It's not like if I phase so much to the left, that's where the object was, because the phase is a function of the position, right? So finer frequencies can only have the effect of the phase shift on finer frequencies is much smaller, because for given 2 pi phase shift, they can only phase shift the width of their wavelength. And so as a result, if you look at a phase map, they are not intuitive. Humans are very bad at extracting information from phase maps. But one useful thing for phase maps is, this is the classic problem of image registration. So how do we register this image and this image? And a lot of times it actually is done using the phase maps. It basically looks for the correlation of the phase maps. But yeah, so in a amplitude spectrum, which is this is the amplitude of the frequencies, a single point on the Fourier transform corresponds to the entire image. So you can't go, this pixel has this spectrum. And correspondingly, if you selected a single pixel and try to get the Fourier transform, it's just DC then, right? Because a single pixel doesn't have any modulation to it. It's just its mean intensity. Okay. Close that. Close that. Okay, so here's our image. So this is where image processing becomes a fun little strategy game, because we have a bunch of different things going on. So it just becomes a game of how can I define what I don't want and want to get rid of from what I do want. And so looking at my image, one of the first things that really stands out to me is I have this sort of weird wavy ripple pattern. And that's low hanging fruit, because a smooth ripple pattern is guaranteed to be low spatial frequency. And my bacteria are very high spatial frequency, right? They're just sharp little points. And so it's like, okay, well, that's, super low hanging fruit is I can get rid of this ripple pattern first and then just see what I have left to deal with. So to do that, I just duplicate my stack. And go to filters. And remember, we want to make a low frequency representation of our image. So those we want to make just a background representation. And the key thing to, gauging, well, how big do I make my Gaussian blur is you effectively want to go, what is the the largest blur it can go to that doesn't change the background pattern. So we're going to use the same trick to that dandelion. So we're going to go to Gaussian blur. You start off really small, like 2. You can see, we haven't really changed our background. So not the fine detail in the background, but this sort of large scale ripple pattern. And we can jump to 10. And now you can see we have still have that ripple pattern. We're going to try and ignore the bacteria pixels and just think about that ripple pattern. So I see like this wave right here. If I remove it, I still see that same wave pattern. And now you can see I've gone too far, right? Because even my background wave pattern is starting to smooth out compared to a 10, right? So now it's not quite, we have more detail of the background. So we're going to process it. So now we have the backgrounds, that nasty wave pattern with not much of the bacteria. So let's go to image calculator. So remember, we're always whittling away. So image calculator is how we whittle away. We're going to take original image and subtract the background ripple. So we're going to do a high pass filter is what we're doing. And there we go, right? So you can see now we still have noise, but we got rid of, at least to start with, that really nasty, ripple pattern we were seeing before. Okay, so step 1 complete. So next thing we can look at is, well, the next noise I'm seeing is I'm seeing this sort of salt and pepper noise, right? This kind of very, very high frequency, like super high frequency, single pixel. And my bacteria aren't single pixel, they're at least, a few pixels in size. So now I can kind of play the opposite, which is, I have these sort of outlier pixels. And so in that case, we go like, well, that's a classic median, which is, I don't want to spread out these bright points. I want to kind of have these overly bright points become the value of what their neighbors are. So we can go to median filter. And same idea, it's just, you just like kind of like, any sort of surgery, you don't want to remove more than you possibly have to. So you always want to try and keep your filter as small as possible. So just, in this case with the median.
Hey, Ben.
Yeah.
Sorry to interrupt. Before you do this, can you cancel that and just play around with the brightness? Because it's really hard to see anything on the image you just created, the image stack.
Oh, yep.
And also, yeah, the bandwidth for the podcast is not so great. So as you play around with the movie, it's hard for us to see the changes. It takes like a second or 2 for things to change.
Yep.
Thank you.
Okay, that's a little better. Yep, that's good. Okay. So what we're going to try and do is the audio bandwidth okay? It's just a video. Okay. Yeah, so what we're going to try and do is remove those outliers. So you can go to filters, median. So you can see 3 does a really good job, but we always want to go as low as possible. So you can see 2 is also doing a pretty good job. You try 1, and 1's just fusing it together. It's not even really removing it. It's leaving too much behind. So I'm going to go ahead with 2. And the reason going ahead with 2 is because in this case, we want to track puncta. And the thing I'm worried about 3 is 3 is trying to fuse our puncta together. In other words, it's removing the information we care about. It's too big. So I can go with 2. Okay. Let's clean that up, make it a little brighter. Here we go. Okay, so now we've further suppressed our background compared to our original image. So the next thing we need to do is we still have this sort of background signal, right? That's kind of flipping around. So now I can think about it again. Like, well, if we look in space, the catch is now we've kind of got ourselves in what we think of as a corner, which is the sort of feature, the size, the intensity gradient of our background now looks just like the bacteria. So that tells us in position space, we're out of options. Our background looks like our signal. So now we need to think outside the box a little bit. And so one thing you might realize is, well, in space it looks the same, but if you look in time, the bacteria tend to always be in the same spot. But the signal, frame to frame, dramatically jumps. So we can see that by taking orthogonal stack, right? By looking at orthogonal projections, we can see, it might be a little hard to see for you guys, but in every single frame, the background noise jumps. So in the Z projection or the time projection, the background is being modulated at a very, very high temporal frequency, but a real signal is not. So you can be like, aha. So we might be out of options in the space domain, but we still have the time domain that we can use to our advantage to remove this background. So we can do that. So what we're going to do is we're going to go to filters. So this is where these 3D filters come to your advantage. So this allows you to access so all of these are always in 2D and only in a frame. So in your space domain. But these allow you to access either Z spatially or in this case, time. And so we're going to do a median. So basically what I want to do is these are outliers. So I want to return them with above and below that point. So the way we can do that is we just say, I want my space to be 0. I only want to do this in time. And this is really important to keep in mind with movies and doing 3D filters, is if it's a movie, you have to make sure that you filter space and time independently. Because if I do something like this, I'm now convolving space with time. We're trying to combine apples and oranges together. So you have to be really careful, make sure you touch one, then the other, to leave them independent of each other. Okay. And we're going to do bare minimum, the smallest touch we can. So you hit OK. Increase intensity. And now you can see we're doing even better now, right? So we're really starting to suppress that background relative to our original signal. So the next thing we can do is we can try and threshold away the background. See if we can get away with that point. Yeah, so this is the key. So you can see that now that our background is substantially dimmer than our signal, which it wasn't in the first case, we can now do something as simple as just using the intensity dimension. So we did space, we did time, and now we're going to use the intensity dimension. You can see using intensity, and a great trick to do is to binarize it like a mask, like this. And you can really tell where you want to do your cutoff. That looks pretty good. Okay, so now we're just going to threshold, and the quick way in ImageJ, the threshold to do an intensity cutoff is just adjust it to how you like it and just hit apply. Hey, yes. And now you can see our new intensity has removed everything below those intensities. Okay, so one thing we could do at this point is you see we have a little bit of a registration issue, but to save time, I'll not do the registration. Actually, I can do it. So you can see that our sample is drifting a little bit at the start. You can tell that by the whole global frame is drifting. And there is no way we could ever register this original image because there's just too much background signal. It's going to try and register that. But now we have a chance. So go to plugins, registration, and we're going to do stack reg, classic registration. And these are degrees of freedom. So for speed, you always want to minimize the fewest degrees of freedom that describe your issue. So in this case, our image is only translating. It's not like rotating. So we're going to do only translation. And so this way, we can correct for that Z drift and keep it aligned. Okay. And so now you can see we got rid of that Z drift, sorry, the XY drift, the lateral drift. And now we're only looking at the trafficking of these proteins within these bacterial cells without the additional translation of the whole field. So you see we have one last little issue left, which is we still have a little bit of the salt and pepper noise left. So that tells us we just go back, grab our medium filter, and just do a tiny little excision, and we can do, again, bang for the buck. We're getting a nice suppression with that last little bit of median. So you hit OK. And so now you can see we just used two types of filters, right? We just used a Gaussian blur and a median filter. In this case, we did both spatial and temporal. And the end result was we were able to fully remove that background signal and get to here with like no fancy deconvolutions or deep learning. And the reason we're able to do that is because we had enough information in our original image that even after we cut all of that background signal left, we still had enough information to get the original image. So this is just something to keep in the back of your mind is even things that look very intractable like this, just as long as you understand what these filters are doing, you can start to think about it as like, how do I define this removal? And the nice thing is, right, then all you have to do in the end is, right, you just go to your nice little macro recorder tool, right, perform those steps, have as a macro, and then you can just run those steps on every image automatically. And then all of these images that originally look like this will be filtered out, and now you can do your analysis. Okay. So any questions on that?
None so far, but I can bring them up if they come.
Okay, so now let's do deconvolution. So now that we've done Fourier transforms, we're at deconvolutions. So what is a deconvolution? Right, so deconvolution is you're trying to, so your image is a convolution of what the actual original signal was convolved by the optics of your system, right? So your original signal could have been a single fluorochrome point, but due to the diffraction limit of your optics, that point is going to come back to you as a Gaussian, the point spread function. So you go, aha, if I run that backwards, there's deconvolve it, then I can remove the point spread function effect from it and get just that point back. So you can do that even in ImageJ. So let's close this. So now we're going to grab our classic dandelion image again. And just to make sure, so I'm going to do a little custom modification. Let's write this. So, no, this is like that trick where the magician, signs the cards. You make sure I'm not just reopening the same image. Now we have a custom image. And I'm going to grab my point spread function. Here's a terrible point spread function, right? Giant Gaussian. This is, our image is going to be super low resolution. And so the key thing is, just like how we have a calculator for things in position space, which is our image calculator, we can also do the same things as an image calculator in Fourier space. So if you go to FFT, you can see there's this tool called FD Math, and this is effectively your Fourier transform calculator. And so to convolve two things is to multiply their Fourier transforms to each other. So if we take our image and we convolve it with a point spread function, we're going to hit OK. And we get this super blurred version, right? This is equivalent to having done a huge Gaussian blur. So like there's no, if you looked at only this, you couldn't even tell what the image was. The fact they wrote anything as corner is completely gone. But what really happened in Fourier space? So if I take the Fourier transform of this image, you can see we get this sort of characteristic pattern. If we take the Fourier transform of this image, we get these concentric rings because it's a Gaussian. If we take the Fourier transform of this image, oops, and raw. That's a sec. Yeah, something weird happened. This again. Process. FT math. Convolve. Yes. Okay. Options. Yeah. Process. TFT. Yes. Yeah, but sometimes it's easy to accidentally click on these when you have the pencil tool. It'll mess up your image. There we go. Yeah, I'd accidentally clicked on it with a pencil tool. So if you look carefully, you'll notice that the convolved Fourier transform is a simple addition of these two. And I told you it's multiplication. Remember, these are the logs of the actual Fourier transform. So if you remember back to like high school math, if you multiply two numbers, that's equivalent to summing the log of those two numbers. So since these are all logs of the Fourier transform, the result of our convolution is a simple summation of this plus this. So you can see these sort of streaks are right here, and we also see the concentric rings. That's it. That's a convolution. So now it should be really apparent. Well, what's a deconvolution? It's subtraction in log space or division in the original space. So it'd literally be, right, we should be able to get back to this image by just doing, this Fourier transform minus that Fourier transform. So we can close this, and close this, and oh no, we just lost it. So, this is what I call the CSI deconvolution, because now we have there's no signal there. There's nothing left. So you'd expect that this deconvolution might return something, but it shouldn't return the full image. But you can try and see what we get back. So we're going to go to FFT, FD math. We're going to go to take our result, and we're going to deconvolve our result with our point spread function, right? This blurred function. We're going to say, okay, wait a minute. That's like, that's basically resolving atoms, right? We don't even see it here, but when we did the deconvolution, we got everything back. So this is a mathematical deconvolution. So the information is still there. And so the way to think about this is almost like our password. If we get the right password, then we'll get the original image back. So now that we know that that this is mathematically possible, why on earth can't we do this with our microscopy data? And so to start with, one thing I'm going to do is I'm going to duplicate this, and I'm just going to convert it into a 16-bit image. So kind of more in line with what we would take on a microscope. So it's the exact same signal, the exact same image. I didn't change the contrast or anything like that. And I'm going to try and deconvolve it. Go to result. So I'm going to try and deconvolve result 2 from the same point spread function. And you see the vestige of the signal, but now it's a lot worse. And then if I go even further, so this gets into gathering as much information about your image as possible. So this is the exact same thing. It's now just with 8 bits of dynamic range. So with 8 bits of dynamic range, if I try and deconvolve it, there's nothing left. You couldn't tell anything about the original image. So if we go back to then how did the original one perfectly deconvolve? Did I lose it? Close it. There it is. So if you look up at the title bar on the image J, you can see the pixel values of this are in the hundreds of millions. This is mind-boggling dynamic range. To get the equivalent of this on, say, a confocal microscope would take weeks, if not months, to collect this intensity somehow without your sample photo bleaching. This is an untenable dynamic range. And the other thing to keep in mind is the other huge advantage is a point spread function. In this case, this is a simple convolution, is the same across our entire sample, which is not true in the real world. So that's two things against us. One, we cannot collect billions of photons for every single pixel in the image. Our fluorochrome is going to be long gone. The sample is going to be incinerated. You basically cooked it. And the third problem we're going to run into is, in this case, we know effectively our point spread function at impossibly high. So in this case, equivalent microscope would be like we know it at like single nanometer resolution. But the only way to know what your point spread function in your sample was is to measure it, or to guess, which is the iterative deconvolution. But the catch is, well, what are you going to measure it with? You're going to have to measure it with the same optical system that you're using to collect the original image. In other words, it's the accuracy you can get your point spread function is bounded by the same accuracy you're using to get the original image. So that's the third factor that's kind of running against us, is there's a limit to how accurately we can know the point spread function. So yes, if we could collect billions of photons from every pixel in our image, and then have the point spread function be perfectly uniform across the entire image, and then measure the point spread function at atomic resolution, then mathematically this would happen. But that's fundamentally, we can't do that. So usually when people are doing deconvolutions, they're doing what's called an iterative deconvolution, which is effectively a computer trying to guess what the original point spread function was based on the feature space in the original image. So that's why you have to be really careful. Same thing with like using deep learning, is if you over iterate, it'll make your image look better and better, but that's a computer drawing something that looks to you subjectively good, but it's getting further and further away from what the original image was. So any questions on deconvolutions?
Yeah, two quick questions. Yeah. I'll go with the latter first because it's directly relevant to this, but does ImageJet deconvolution plugin allow you to utilize experimentally obtained point spread functions?
Yes, yes. You wouldn't use this deconvolution tool, because this is the mathematical deconvolution. But there is, I don't know if I have it on here, because I don't remember if it comes built in, but there is a deconvolution plugin that actually allows you to measure the point spread function, have the raw image, and there's even a point spread function generator. So even if you didn't measure it, you can have it generate based off of your optical system what the point spread function should have been. And then we'll do the deconvolution for you. So yes, but you wouldn't use the mathematical deconvolution, because to do it based on point spread function, one, point spread functions are three-dimensional, and two, you need to normalize the amplitude of the point spread function to the amplitude of the image. But yeah, they're plugins but effectively that's all you need, right? You just need the point spread function and the image. Oh, there you go. Someone posted it. And also should get into that. You definitely kind of what I was hoping to get at, and should get across now, is you really want to read up on the papers that involve these deconvolutions, because it's almost always going to involve some degree of a modeling of the point spread function. You can directly extract it, and you can directly extract it, but sometimes a little bit of fitting helps nudge a little bit further, but it helps to know what the algorithms are that are being used. So a lot of times in these deconvolution plugins, you can also choose the sort of model fitting algorithms. And on top of that, hopefully the point got across, that if you want to deconvolve, so like say you're also doing like an area scan, right? Area scan is a deconvolution. Dynamic range is everything. The more, like you just saw, the more dynamic range we had, we got more and more detail back. So like an 8-bit image, unsalvageable. 16-bit image, we actually got something back, and we could tell what we're looking at. And 32-bit unlimited image, we got the full detail back. So when you're doing deconvolutions, whether it's on area scan or computational, make sure you get as much information you can, even if it means like summing multiple frames together. The more dynamic range, the more detail you're going to get back. Real detail, not simulated detail. Okay.
There's a general question about your entire talk, I believe. Is it possible to get a step-by-step procedure of the sort of clicking you've been doing to do all the image analysis that you've been doing, so people can practice with their own images? Is that in the presentation that is shared?
Yep. So one, this is being recorded. So like Holly said, in about 1 to 2 weeks, this will get posted. But if you look at the posted comment up top, there's a link. And so that link is to this folder. So it has both the slides, but also has the macro. So if you take the macro and just drag it in, it'll load it, and then you can just run it. So you can go through that same demonstration that I just did. So you just hit run. You just reference it back to the folder. So basically you just reference it back to this folder because it needs these images to run. You just hit select, and then you can go through all the examples. And on top of that, all the example images are in. So if you want to play around with, say, this noise example, like this is your answer, and then this is the raw input. So you can actually take these raw inputs and then play around with it and see if and this is like not the answer. I should say that too. This is an answer I came up with. There's probably an even better order or better size of filters to use. But yeah, to just get a sense of playing around with. So everything here is in this folder, and it's in that bit.ly link at the top of the chat. Okay, any other questions?
I think the rest are mainly comments.
Okay, so one last thing to get to, kind of one nice little icing on the cake is, oh, yes and no. So there's one trick you can do in ImageJ that I think is probably the most underused, but it's helpful to understand, which is we did, Gaussian and median, but you can also make your own convolution kernels, right? So the convolution kernel is the sort of matrix of values you're going to multiply your image by. And here's a classic one you've probably seen in Photoshop and stuff like that, called embossing. So here's our original input image. You can see if you emboss it, it looks like that sort of 3D DIC effect you get. And you can actually do that with just a simple convolution kernel. Now, it hasn't changed the information. I should point out, this is not DIC. DIC actually can do additional things. You can do optical sectioning, stuff like that. This is not, but it does make it a little bit easier to see features. So this is more like a for humans thing than a for analysis thing. But we can do this. So we're going to grab our image. Let's see, where's our cells? There we go. So here's our input image. And so the last one to do custom is under filters. You can see we have this option convolve. This is, remember, convolution is just taking two matrices and convolving them together. So in this case, we're just going to give our own matrix, just to enter it by hand. So to emboss, really all you're doing is you're just taking the derivative of the image, which is exactly what DIC is doing, is just taking the derivative of the image. So sharp rising edges intensity are encoded one way, and sharp dropping edges are encoded. So you can say like rising intensity is bright, dropping is dark. So do that. So in this case, we're going to do it diagonally. Oops. And this is just how you enter in by hand. So we're going to say -1, 1, 1. And on the last row, we're going to say 0, 1, 2. And so what this is going to do is for every pixel in the image, it's going to take the pixel in the middle, multiply it by 1, take the pixel immediate to the left, multiply it by -1, and the one above, and then the one diagonal is going to multiply by -2. And so you can see this is going to give us a derivative back. So if it went from dark to light, going diagonal down right, it should get brighter. If it went from bright to dark, it's going to get darker. And voila. So that's the embossing kernel. So when you see these fancy, embossing convolutions or other stuff, it's actually a lot of times it's very, very simple convolution kernels such as these. So that's it. Hopefully this helped to get a sense of, the filters in ImageJ, but also more importantly, to get a sense that, you don't need, trainable Weka or stuff like that to do your filtering. And on top of that, like when you use algorithms like trainable Weka, should I remember what trainable Weka is? I think it's under segmentation. Yeah, so you use adaptive algorithms like trainable Weka segmentation. You'll notice that it has a bunch of filters and settings. And so, really all it's doing is it's doing effectively this trick. It's tuning the size of these filters based on your criteria. But to really understand how to even do an adaptive learning, you need to have a sense already of what sort of feature space best delineates your image from the background. So, it's not a magic, bullet. Instead, you really need to have a strong sense of kind of what's covered here, where you can segment and denoise images most of the time with just basic filters, and you don't need more advanced algorithms. So that's it. So I'm free to answer any questions. Thank you for sticking around. I know this was really long, but hopefully covered as much as people wanted. If any questions, I'm free to ask.
Yeah, and Alex and I can ping you guys in if anyone wants to ask in person.
Ben, there's a comment from Bram about the top hat transform. If you wanna, and Bram, you're welcome to also join if you want to have a conversation. And I think you can just share your microphone, or Ben can just answer from your comment.
Oh, now top hat makes sense. Yeah.
All right, Brad, you should be able to, if you click join the video and audio.
Because I think that top hat might be part of the trainable Weka feature space, if I remember correctly.
Hi.
There's also because I know like the sombrero, which is the difference in Gaussians.
Yeah, it's more or less like that. I think nowadays it's under. You can hear me, right?
Yep.
Okay, so now at new, I think since a few months or weeks, it's under process filters, and then just top hat. If you have it already.
Oh yeah, I guess I haven't updated.
Okay,
Actually, I didn't update because I remember there's that the previous version there was some compatibility issue with some of the macros I ran. So I held off on that one.
Yeah, it's actually indeed. So ImageJ or Fiji still ships with.
Although if it's Fiji, then we should be able to just.
No, it's so Fiji ships with 1.53c ImageJ version, and it may not be in there.
Right, but if it's Fiji, it should be on the Fiji wiki site, because everything on Fiji technically has to be on the Fiji wiki
so
site.
It's MorphoLibJ has it as well. Yeah.
MorphoLibJ is so good, man.
Yeah.
I'm so grateful for that. There's so much good stuff in there.
So we use it. The top hat I use also quite a lot for small DNA damage foci, for instance, in nuclei. That works very well. But then again, that works more or less the same as difference of Gaussians, and that
Yeah.
also works the same as subtracting the rolling ball background subtraction.
Yeah.
Sometimes, so
But the catch is they all have their own strengths and weaknesses. So
yeah,
that's why I love to show like in Fourier space, because a lot of times, especially even just things like mean and Gaussian can look very similar in position space in the image. So people like think they're doing the same thing. But yeah, when you look at like Fourier space, it's like, no, they're completely different.
yeah.
They're changing the information content very differently. But if Morpholab J is what I'm thinking of, is that the guy who wrote yeah, dude,
Yeah,
these are the
there's a
best
lot there.
tools ever. Morphological segmentation.
Yeah.
That is so good. And actually, I use this all the time for tracking objects. It's so good for
Okay.
that.
Yeah, the market control watershed, that's great, yeah.
Because you just
Then,
put seed points in your first frame, as long as it's a binarized mask. The marker controlled watershed, the way you think about it is like you're pouring your seed points down through your movie.
yeah,
And it will naturally, so even if you get like a merger and a split, the marker controlled watershed will actually like segment the merger and the split for you.
that's
So this
good,
is
yeah.
such a good tool for tracking objects. I love it.
Cool.
It's so good. And yeah, even classic watershed, like
Yeah, it's
yeah.
written by what is it, David Lackland and Ignacio. I can't pronounce his last name again.
Yeah.
But
I definitely say like
I
Morpholab
don't
J
know,
is
right?
like
I think.
it's like a workhorse library, man. I go to it
Yeah,
so
yeah.
much.
And nowadays, Robert Haas has also written a few things in CLIJ that sort of resemble those operations.
Although, we all know what the best plugin library is.
This one.
It's huge a self-plugging right there.
Okay.
my one plugin, the hop circle
All
transform.
right. Yeah. Sorry, I
But
didn't know it.
it's used in material sciences. It's very rare, if ever, used in biology.
Okay.
It's an algorithm that can segment circles even on extremely noisy backgrounds, but they have to be perfect circles.
Okay. Well, could have its
But yeah,
uses.
that in the other library, this tool, so good. So much good stuff. Like all the kernels in here are round, not square or cubes. So they're actually like properly shaped convolutional kernels.
Yeah.
The 3D draw tool is super helpful. So you can actually make 3D objects to test your filtering algorithms. Yeah, so this one's also great. Love it.
Yeah, there's too much good stuff.
There is. And I think that's the biggest problem with ImageJ too, is like there's so much. I think people get overwhelmed. And that's where again, I think it's helpful to point out to people is like don't worry about this yet. Master this first. And once you get really comfortable with this, and you'll understand like, oh, I want to be able to do this one other thing. And I've learned with ImageJ, 99.9% time, if you want to do it, someone's implemented it.
Yeah.
So literally, you just Google it,
Very
like
true.
how to do this. It's like, oh, this library has it.
Yeah. You go to the forum.
The only thing that frustrates me is that you now have to download Transform J. It's not. It doesn't come with Fiji by default anymore.
Okay, there's
It's like,
no update site for that?
no, there is an update site for it, but it used to come like packaged
Okay.
with Fiji.
Right.
But now you need to get it separately. And like that's such a fundamental tool. That seems such a shame that it doesn't come prepackaged.
I never use it actually. I see
The
it then.
best one is I think it's the turn or is it the rotate? Because one of them does the orthogonal transforms. So if you want to like go from like an XY with Z being slices to like an XZ with like Y being slices, so if you just want to rotate your stack in 3-dimensional space, Transform J is perfect for that. It's a super fast implementation of it.
And it's basically the same as the reslicing then, but then faster probably.
Reslicing?
The
Is that another
reslicing,
plugin?
I think it's also does roughly the same, and that is standard ImageJ, but it's really slow.
Yeah, no, Transform J is like instant. It's just super fast remapping. So yeah, Transform J is effectively the 3-dimensional version of your transform menu. So the other transforms I don't use, but that 90-degree transform is immensely helpful because so many things are easily segmented in the XZ dimension